This is the second lecture for Chapter 19, which is Thermodynamics, and we're looking at some examples like we did in the previous lecture for some changes in entropy. So for some example molecules, we have a 1-carbon chain, a 2-carbon chain, and a 3-carbon chain. And notice how the entropy increases. The only thing that's changing is the molar mass, or in the structure a little bit, but we see that the entropy changes with molar mass. Got it. So we can do the same thing we did back with enthalpy and just look at the sum of the products versus the sum of the reactants, taking into account the coefficients in the equations. And we're pretty good with that. Looking at a combined equation, we're working towards making a combined equation. Remember, we called this enthalpy, Q, for the system, is the enthalpy at some given temperature, as long as I'm at constant pressure. So easy enough. We're going to use this here in another equation, which is right here. This is a substitution we're going to make into. So we're going to be substituting the value of negative Q, which is the opposite value of the enthalpy gained by a system. So here it is again. And again, if it's spontaneous, we're positive. So here's the substitutions. I won't spend too much time going into this, but here is that substituted value we just put in. And if we rearrange the terms, we're going to get this bottom equation down here at the bottom at some given temperature. So moving it around one more time, I guess we'll see the final equation here in a second. This little picture here is a guy named, it's Joshua Willard Gibbs. And he is the first PhD recipient from an American college. And he went on and developed some of these ideas of free energy. So he put this equation here together. That last term we saw on the previous slide, right here, we're going to change this term over to delta G. So we'll see that in the last equation here in a few moments. And delta G has really no life onto its own. Its expression is just a comparison of the enthalpy and entropy value at some given temperature. And we can see how a reaction can be spontaneous in the picture here from either direction, from the products or the reactants. And so, for example, if it's spontaneous in the forward direction, it's non-spontaneous in the reverse. But either one is going to work until eventually you get yourself to equilibrium. And at equilibrium, the delta G, or the Gibbs free energy value, is going to be 0. So we can see how this can express for whether reaction is spontaneous or not. So the more negative a value, the more spontaneous a reaction is. So we can find those terms exactly like we did for the enthalpy or entropy, just doing the subtraction of the products to the reactants and looking at the coefficients as well. And this a little symbol here, I guess we haven't mentioned it before, that little circle means we're at standard conditions, which is 25 degrees Celsius. So it has to be that way. And I can just grab numbers out of the back of the book, put them in this equation, and that'll tell me whether reaction is listed as being spontaneous or not. The more negative, the more spontaneous. So here's the final equation. So notice that entropy and enthalpy are both at standard conditions, 25 degrees Celsius. But if I vary that temperature, this is why I'm not using the previous formula we had on the other slide. If I vary the temperature, that will tell me how this reaction is going to play out, whether this is going to be negative, spontaneous, or positive, non-spontaneous. And notice that these, the enthalpy and the entropy are different in sign. So the temperature really is going to have a bearing on how this reaction proceeds. Excuse me. So we already kind of went into this. I won't spend more time on it over here. And this is just a relationship of these different cases where enthalpy is negative and entropy is positive. I won't spend time on this, but you can pause the slide here and take a look at how these will relate. Really the main thing you're focusing on here is how is this going to relate to delta G. And all these values, this is a little negative here, how all these values will compare. And we'll talk about this in class as well. So this next equation is, and how does that affect the spontaneity of a reaction? So we have to have our full equilibrium expression, which Q is just something that's going to be equal to some various concentrations or pressures that are going to be moving into an equation. And if you look at this bottom information there, it says, well, what if I was at these kind of standard conditions? Well, standard conditions for equilibrium in this expression are going to be 1 molarity or 1 ATM, and those are the ones that come to mind, but I think those are the ones we have there. So if all those values end up being 1 and 1 and 1 and 1, that's going to end up being a natural log of 1, which is 0, which means all of this is going to go away, and you're simply left back with this expression. So the change, or the equilibrium, this is going to be equal to what it is at standard conditions. So if I was not at standard conditions, this would just put it right back to it, if everything was at standard conditions. Moving on to the next one. If we were at equilibrium, so I'm at equilibrium doesn't mean I'm at 1, I'm at equilibrium, so those values can be anywhere for the different concentrations. How does that compare to the spontaneity of a reaction? So this is a comparison of how this will work out, and you can see how the equations derive, whether you're solving for delta G or you're solving for K. You can manipulate the equation around to get either one. But looking at how a relationship, just to kind of think about what we know about K, actually I'll use this bottom one here, what we know about the equilibrium value and the spontaneity of a reaction. So let's just say, for example, my K value is really large. It's like, just make it up, 2 times 10 to the 20th. What does that imply about equilibrium? It tells me that the reaction is going to very much favor the products, which means going in the forward direction, it's very spontaneous. So what I would expect this value for delta G to be very negative, to be very spontaneous, to go in that forward direction, to give me this 2 times 10 to the negative 20. And then just the opposite. If I was looking at equilibrium and my value ended up being 2 times 10 to the negative 20, then I would expect that I'm mostly favoring my reactants, and it's not favorable at all to go in the forward direction. Therefore, my delta G should be positive. Okay? So we have a couple of equations here and different ways we can manipulate them to get us to the expression, either getting K or getting delta G. And that is the end of the presentation. Done.